Thank you. Hopefully things will be a little less unknown after I finished. So by way of introduction, I like to think about a story about this individual. This is Jose Raul Capablanca, a expert chess player. He was active in the kind of like 1940s, 1950s, originally from Cuba, but here he was interviewed in New York on the sidelines of a chess tournament. And the interviewer asked him, so when you play the game of chess, given your deep expertise in this game, how far ahead into the game tree do you think about? And he kind of surprised the interviewer by saying, I don't think any moves ahead. I only think one move ahead, but it's always the right one. So I've always been kind of fascinated by this sort of anecdote, which obviously is not completely true. Obviously, he does some thinking ahead, but just his kind of introspective sense that he has kind of an awareness of what to do in a given situation, this game, which he's trained for all his life. I think it's kind of interesting to think about, like, what is the kind of mechanistic function of the brain that kind of gives rise to those sorts of intuitions in this sort of complex game. It's also kind of like counterintuitive to me in kind of the broad literature, because we kind of like have this perspective, I think, for many years now, since the time of Craig, which has come up many times even in this workshop, that we do a lot of these sort of like forward simulations and searches and so on when we're trying to figure out what to do, when we're trying to induce kind of flexible behavior. So there's many different sources in this, but Craig in the I think 1940s in Cambridge was a visual neurophysiologist who, as a side job, was also kind of a scientific philosopher. He wrote this book, The Nature of Explanation, and it's sort of like focus, and it was really kind of a book about the philosophy of science, but really what he was focused on as his kind of example for scientific investigation was his own sense of kind of introspection, imagination, reasoning, planning, and so on and so forth. And he kind of has this quote: if the organism carries a small-scale model of external reality and its own possible actions within its own head, is able to try out various alternatives, conclude which is the best of them. More recently, I also include the work of Rosen. I think it's around the 70s and 80s, who kind of really formalized this in a lot more careful and detailed way. And for example, using things like category theory and all that kind of stuff. And just to give a sense of that in the context of like a game, like a board game like chess, what they're saying is, like, in this game, you kind of start at some position, I have some board state, and you kind of generate kind of what's called like a rollout in reinforcement learning, or some kind of simulation of how the game might evolve. If you do that, then you can kind of drive information about kind of future conditions in the game and use that to drive your behavior. So this is sort of idea, this Craig Rosen simulation about this world model, word simulation, and for behavior. And there's kind of two things I want to kind of highlight, maybe, that kind of points in another direction with respect to this sort of hypothesis, and maybe more in the direction of Jose Raul Capablanca's anecdote. And that is, like, from a theoretical point of view, there's a huge problem with kind of multi-causal research methods. It's kind of recursive dimensionality, massive sample variance. There are innumerable algorithms in machine learning to kind of help to address this issue, control variates and positive gradients, kind of learning value functions and so on and so for that to guide search. I'm not going to focus on that so much. I'm going to focus more on the human expertise side of things. And actually, if you look at this literature, this evolved a lot originally from kind of Newell and Simon, which we've heard about from others in this workshop, this kind of problem-solving line of work. There's a lot of descriptions in these studies which kind of describe kind of very qualitatively kind of mechanisms by which kind of human experts in a particular domain might construct kind of novel plans or novel behaviors in the domain. Things like, they use a word like preconditioning, parallelization, situational analysis, the principle of ease commitment. Words that, if you did a kind of Jake Forster style analysis, like a top-up modeling of these books, you'll pick out a topic like insightfulness or directedness a lot. And I think there's kind of a couple of interesting things here. One is that, like, these sorts of, principles of kind of expert human problem solving have not really been formalized in a quantitative way that I think that can be compared in experiment and theory, particularly to kind of, say, artificial systems and so on and so forth. So I think that's one job I think would be interesting to do. And the other is that, these kind of words that, you and Simon use, like insightfulness, directedness, seem much more in tune with the kind of Capablancan style of chess rather than sort of the Craig Rosen hypothesis of kind of simulations. I want to kind of dig into that a bit. Now, one kind of arena in which actually this dichotomy has been heavily philosophized and studied is actually cybernetics. So obviously, I'm not going to go into the history of cybernetics. So going back to Wiener and so on, the study of and kind of theory and philosophy of kind of feedback control systems with a focus on adapting to possible future disturbances. And this kind of line of work that really started in kind of the kind of 80s, and more modern references are Du Bois and Stephen and some of that. They make the distinction between kind of weak and strong anticipation in kind of feedback control systems. So maybe to read one of these quotes, the system described deal with what is called strong anticipation because the current states of these systems are computed from past and or present states and also from potential future states anticipated from these systems themselves and not from models of these systems. What they mean by models of these systems, they mean kind of like internal models that you could like simulate in order to think about the future. So they make this kind of sharp distinction, as I said, between weak anticipation. So prediction of the future given a model is labeled weak anticipation, and prediction of the future not given a model, relying instead on something they call systemic lawfulness, is labeled strong anticipation. I was very curious about what systemic lawfulness could be. They give a bunch of examples here. It's a very abstract kind of cartoon for what a systemic lawful type of inference mechanism for catching a ball on a parabolic trajectory would be. I'm not going to go through this in detail, but basically the ball is kind of coming over here, and you have to find your position here to intercept the ball as it lands. It's kind of imagine that you're catching the ball. So one idea that kind of Craig Robinett posits is that you'll simulate the ball, and you'll kind of do rollouts by this kind of physical system, whereas they kind of derive the systemic lawfulness, which you can extract only from kind of past history of the ball, so that you want to kind of do what is called vertical acceleration cancellation. And basically you want kind of the perceived acceleration of the ball at any given time kind of vertically in the vertical plane to be constant. If you do that and track your behavior such that it matches that kind of verticality constraint, you'll actually arrive to intercept the ball as you would like to do without any course simulations. So they use all sorts of words to kind of contrast these two. So kind of weak anticipation, simulation-based, strong anticipation. I'm kind of injecting the word intuition-based there, consistent with the kind of Capablancan perspective that I kind of started with. Weak anticipations tend to be kind of slow. These words like prediction, simulation. And I think nowadays we kind of contrast a world model type approach, weak anticipation, with a systemic law, whatever that means, and a strong anticipation approach. As an aside, I think it's interesting. I'm kind of curious if anyone else has any thoughts on this, because I'm reading a lot of this literature myself, coming back through the kind of 70s and 80s. It really taps into this, these issues in kind of philosophy of mind, where they actually refer to kind of weak anticipatory mechanisms as being subject to an intelligence loan problem. What they mean by that is the kind of intelligence in the system has been loaned by a kind of conceptualized world model that they think that has to be kind of paid back somehow. And in some sense, they think of it as like intelligence homunculus. That's the kind of cybernetic perspective. So I kind of found that kind of quite interesting, not least because some previous work I did is very much based on this kind of weak anticipation perspective. I also found it interesting from a human perspective because I think it's a bit of a kick in the teeth for humans. I'm a human chauvinist. I think I'm special with my kind of introspective world models, and I can internally simulate, and I'm very smart, and so on and so forth. From the cybernetics perspective, that's seen as sort of the weaker element of anticipatory feedback control. So one thing, that's sort of introduction, and kind of, want to drive in the direction of thinking about, kind of expert human reasoning as some sort of like systemic law process, more consistent with a strong anticipation principle that previously had been really studied in the context of much kind of simpler kind of feedback control systems and so on and so forth. And when I think about that in the context of kind of higher order kind of human reasoning and so on. And I think, really what we'd like to do is come up with a kind of like a general formalism on what we mean by systemic law, the systemic lawfulness in the context of kind of planning and reasoning problems, specifically, what we call market decision processes. And what I'll kind of talk about a bit is sort of a particular state representation, dynamical system that has certain properties that I think one could construe as systemic law, and has some kind of nice normative properties that then will kind of feed back into the principles of human expert thinking that were qualitatively described by people like Herbert Simons and so forth. So that's sort of the strategy. And maybe just see a couple of examples to contrast these two approaches. This is a kind of a grid world, which is sort of like a very simple type of market decision process. It's sort of like a petri dish of market decision processes where you study kind of elemental manifestations of algorithms to solve market decision processes. So we'll see a couple of these. This thing here is the start location of some agent in this world. This is the goal. The job of the agent is to navigate to the goal. Obviously, he has to get through this sort of like bottleneck thing in order to get there. If you do your world simulation, this is like a essentially reinforce. It's a type of stochastic policy gradient algorithm. It takes a long time. You can do lots of simulations. It kind of goes all over the place. Eventually, you can see in this kind of like heat map approach, you see kind of like tracing out some sort of path that you could take to get from the start location to the goal location. So in contrast, maybe something that's a bit more, we say, more kind of strongly anticipatory is something like this, where what I'm kind of portraying here in this blue scale is sort of the distribution of possible states that the agent might occupy in this world. Starts with has no knowledge where to go, so it starts a random walk. So it just looks like a kind of diffusion away from the current position of the agent. And then if you kind of run some kind of like strong anticipatory algorithm, where instead of kind of simulating, it has some sort of notion, the systemic lawfulness, that sort of can construct a more kind of directed inference process, which is more which is based on its kind of current state, current representation, without kind of simulation. It kind of seems a bit more kind of direct and insightful in the sense of Herbert Simon and so on. So how do we kind of build such a thing? It's not a terribly complicated method. This is a well-known plot from Sutton Barto, which is sort of the Bible for reinforcement learning. What we just saw first with the kind of simulation model, essentially kind of like a type of Monte Carlo approach. We do these kind of deep rollouts. This is a space of possible algorithms you might use, which kind of vary between like the width of the update and the breadth of the the width of the update and the depth of the update. Whereas kind of Monte Carlo goes deep. We can also do things like dynamic programming. This is reflected in kind of search theories. You get a breadth first search, depth first search, all kind of stuff. All these different algorithms are sort of like in the space here somehow. And what we've find in the bottom right here is kind of like exhaustive search. We try out every possibility in the environment, which is generally thought of as essentially impossible. But maybe there's sort of like a way one can build some kind of dominant system approach, which sort of effectively accomplishes something kind of looks like exhaustive search, but without actually doing all these different kind of rollouts and so on and so forth. So the way to kind of get at that is to kind of think about a kind of, another state space here. I've kind of schematized a graph. Each node is a possible state. The agent can transition between nodes. And what you could do is you can kind of roll out all these into all possible paths in the environment. So you can see if you kind of trace in your mind, I have the trajectory 0, 1, 3, 0, 1, 4, and so on and so forth. And I can roll out every single possible path. Noting that I kind of took care to include a kind of a cycle. So there's a possible infinite number of paths, therefore undermining the possibility that you could do any kind of like exhaustive search in this particular domain, as an example. What you would like to do, really is sort of like max over all these possible paths. So if you could do that, if I had some kind of super intelligent being, I could enumerate all possible paths, and I could just max over them. As I said, there's an infinite number of paths in this domain, so we can't really do that. So instead, what you can do is some type of gradient descent process in this domain. And that's the sort of the kind of algorithm we're going to discuss in simulation in the next few slides. Okay. So that kind of gives us this, if you do that, I'm not going to go into technical details about how it works, but essentially if you do that in this domain, you get this sort of planning process. It's interesting to maybe go back again, if you play it, it's kind of hard to see, but what we can do is we can freeze it at the kind of very first time step and see, what is it that the kind of algorithm changes at the very first time step. So, one thing that one might imagine is if I'm starting in this position, it's kind of super important that the agent gets through this kind of bottleneck here, potentially thinking that is like the most important thing in the domain. That would tend to be called a precondition in the sense of Neal and Simon, in the sense that to get to this goal location from this location, it is a precondition to get through this bottleneck. If I look at consider the gradient at time 0, the first thing it does is optimizes the policy to go through that bottleneck. So it's sort of like picking out a bottleneck as the critical element of the planning dynamics. So where does that come from? To give some kind of like insight into where that kind of gradient, why that gradient can focus on that key bottleneck, you can kind of draw on or relate this kind of analysis to kind of breadth first and depth first type thinking and what's called like spreading activation comes in psychology. So here I have a kind of spreading activation which is manifested, it was called the success representation for those who are interested in reverse learning and mark decision processes from the start location. And if I multiply that by a spreading activation in the goal location, I get this interference pattern in the state space. So you can imagine we had an example of kind of slime moles and stuff like that, spreading out across space. If you're going to do that in your mind, from the start location to the goal location, and see where they interfere, what actually happens is the gradient at time 0 kind of computes that automatically without simulating, essentially. So that's sort of going from, this is sort of a weak anticipatory mechanism to a strong anticipatory mechanism. So sort of like this is explicitly generating these kind of predictive maps of this environment. Whereas on the right, it kind of like just falls out of the dynamic system. So in contrast to kind of where simulation approaches, these take a long time basically to converge and pick out this sort of precondition in the state space. It's on the order of like 4,000 simulations. Okay. So another type of kind of emergent dynamic in this algorithm, which is kind of interesting, is that, again, we have a new Petri dish here, where if the agent starting this location here has to get into this goal in this room, this is the 4-room grid world, again, another kind of elementary mark decision process to kind of elucidate the kind of implications of these algorithms. If you run the algorithm in this case, it kind of like highlights the kind of bottom right room, which contains the goal location, and it kind of works its way back to the start location and sort of deletes the states in the target room that are not relevant to its behavior. So maybe to see it again. So initially you get this sort of like increase. When it goes blue, it's basically the algorithm thinking I need to go to those states. When it goes red or kind of whiter, it's saying I do not need to go to those states. You can see it's sort of through the kind of strong anticipatory plan dynamics, it sort of creates this abstraction of the room and then sort of deletes it through time in the single dynamical system. So here you have the simulations, and okay, this must be different ones, but anyway, it's fine. Let's go back to this one. So again, it sort of creates this kind of abstraction, this room, this kind of emergent room representation, figures out how to get to this room, and then once it's done with that, it kind of deletes the room. So one way to interpret that is that initially when the agent has to get, sorry, yeah.
Did you try running it on something like 100 by 100 grid? Like how big will this?
I mean, we've definitely done 100 by hundreds. I think we're kind of like, I think you can run the vanilla thing using jacks and stuff on a GPU in like thousands and thousands. To scale it, to proper non-Petri dish style state spaces, this is kind of a long discussion, but we're thinking of various strategies. One strategy we like is kind of synthetic gradient approaches. We're basically trying to feed forward network to map from a position to a vector field in policy space, and then you can integrate along that vector field. That's sort of the kind of general strategy. Yeah. I still can't say, for example, it's a whole other set of questions to ask whether after doing that, you still retain these sorts of like abstraction features and all kind of stuff. It's, so unclear at this point. Yeah.
Would you mind going back one slide? So
Sure.
it also looks like the gradient is going basically through the obstacles, if I understand correctly, right? So it's coming up with a solution that maybe, again, like a human planner probably wouldn't take, but walking along sort of the obstacle on this path rather than just doing one turn, like going, for example, right and then down.
Sorry, can you say that? Where are you pointing to? Here?
So the path that it comes up with, if I understand it correctly, is not something, maybe that like a human planner would take right, in the setting. So you probably would just go right and then down, rather than doing many turns, right?
Okay.
And I think it's arising from the fact that the gradient seems to be spreading basically sort of through the obstacles. So I was just wondering if this is a limitation of this.
So you're saying like a human might go here and down?
Yeah.
Yeah.
Rather than doing many turns. Right?
Yeah, no, it's a good point. I think, I don't think it's a limitation. I think what's happening there is, if I penalize the terms, for example, it would kind of do this, right? So if you have sort of like a penalty on the policy complexity, it would maybe use something more human-like in that sense. We're not using that here, but sorry, yeah.
But still, I don't understand. So why the center of the top right room is not the same color as the corner? So the corner of the room is blue, and the center is orange, right? Why are they different color?
So which room are you talking? This one?
Right.
This one?
Yes. So the center of the room is as good as the corner.
I see what you mean, yeah. So it's not distinguishing here. That's interesting, yeah, I see what you mean.
First to go through the corner.
Yeah, I see what you mean. You're saying that it's the same number of states.
The same number of
This is equal.
Yes.
Yeah.
So why does it prefer to go along the wall?
Yeah, it's interesting.
One reason could be that there's fewer actions if you stick close to the walls. So
Yes.
your decisions are half in the exact corner because you have only 2 instead of 4 actions. And if you hug the walls, basically you at least reduce your action space by 1. So that could be one reason.
I think that's exactly it, yeah. Sorry, I forgot, because what we didn't do, the way we should account for that in the future is you can add actions here that you bump into the wall.
Yeah.
And actually in the simulation, we didn't do that. So actually, yeah, as you said, this is essentially like it's easier to solve these decisions, so it kind of gets biased towards them. Yeah, let's go. Thank you very much.
So question, could you maybe intuitively explain the difference between your method and successor representation or SR-DINA or any?
Yeah. So I think there's a strong connection, and the connection is that this approach is essentially kind of higher order successor representations. So instead of using kind of the SR itself, actually when you look into the kind of mathematics of gradients of these gradient, like you can analytically compute them, they're actually sums of squares of SRs and cubes of SRs representations. So I think the kind of bigger geometric picture is the SR for policy value. You have these sort of like sums of SR squares of policy gradient, and then you have SR cubed for like the kind of curvature of policy space.
Is it mathematically similar to the fact that like the grid fields would be the eigenvectors of the SR and the relationship between those?
Sorry, can you say that again?
So in eigenvectors of SR helps to identify bottlenecks also, and sort of, I wonder whether there is some mathematical similarity, especially since in the brain one idea is that maybe hippocampus is SRE and entorhinal cortex is more eigenvector of it.
Yeah, totally. I think it's a very interesting direction. In terms of like the kind of hierarchical aspects of it, I think what probably will happen is that I think what this is picking up on is similar kind of bottlenecks you get if you, so for example, threshold the second eigenvector, the SR and stuff like that. But then what you get for the kind of, so it kind of keeps that in the picture. But then what you also get in these higher order ones, you get sort of like SRs for sort of like, you get sort of like abstractions between states that are not contiguous.
Got it. Right? So more like eigenoptions actually. Yeah,
I think they're more, I think you can pick out things like that. You get like, let's say emergent eigenoption type things. Yeah. So yeah, thanks for the questions. Okay, just to finish that, I think it's interesting, kind of reinforce the point is that although I kind of showed you a picture of these dynamics in sort of the state space diagram, really what we want is trajectories that we're actually going to follow in our behavior. And as what I'm kind of illustrating here is that if I'm navigating the top left room to the bottom right, at time 0, where I haven't done any planning yet, I can just random walk around the state space. But then after a time, I sort of optimized my behavior to get into this room. Okay, so sort of like I get into this room. After that, I don't know what I'm going to do. I'll just random walk. But the first thing I need to do is get into that room. And then over time, it kind of refines your policy within that room, right? And you can see this in sort of this. This is the SR, which is sort of like your kind of future possible occupancy in the state space. What you see here is that this is color-coded by state here. What you see is that the state in this room has this kind of non-monotonic structure, where initially all the rooms are kind of treated as one, and the agent or this planning process sort of decides to go into one of these states, and after time, it sort of starts removing some of them from its future occupancy. Yeah.
You're looking at this problem in a discrete sense.
Yeah.
But if you were to, instead of this interior walls, you would put high mountains and a pass, you can cast it as a problem in the Riemannian manifold.
Okay. So
It's, you have a definition of the distance between 2 points. And the distance to go over the mountain, it will be very high. So you can have a smooth model which will replicate this.
Yeah, I agree. I mean, we're currently doing a lot of work on like adapting this continuous control setting, and also more broadly, I'm kind of excited about really looking into the geometry of it and how kind of different elements of the structure of the dynamics in this.
Similar problem exists in ray tracing.
I'm sorry?
In ray tracing.
Ray tracing, okay.
Well, suppose one of these initial positions, you put a light source.
Okay.
And you want to see how much light gets into the other room, right? So you would send a pack of rays. Some of them will penetrate.
Yeah.
And then you can build up. So it's a similar thing. There's
I guess
some analogy with that.
I guess the ray tracing analogy I would say is sort of like ray tracing is like activating like an SR representation. It's sort of like
There is a similarity.
Yeah, I agree. Yeah, it's interesting. Okay. Probably have to go a little bit quicker. So one thing I like about this is that it kind of makes it accessible to kind of higher order manipulation. For example, what I want to engage here is kind of what we call like situational analysis, which is essentially saying like there's one thing to plan in any kind of situation to solve my precision process and at a kind of global level and figure out all the different states I need to optimize in the state space. It's another thing to say like I want to figure out what I need to do right now. Okay, so maybe to go quickly to this example, the focus here was initially to get into this room here. So sort of like in the initial dynamics of the model is sort of to figure out how to get into this room. Then after that, it kind of figures out as it goes, what it needs to do. We're going to kind of dig into that a little bit more. So for example, in this like a simple decision tree, you have a start state here, you have a goal state you have to get to, you have to go through states 2, 4, and so on. So it's just a simple binary decision tree. If you run these dynamics, it optimizes the states backwards from the goal state to the start state. So you first know what to do state 4, then 2, then start state. Essentially, what I just want to point out, so actually if you put on a kind of a higher order, a second order conditioner on the gradient, like sort of like a type of Hessian in some sense, and do second order optimization, you can actually select which state you optimize for through the planning dynamics while always retaining the guarantee of global optimality. So it'll always converge ultimately to the optimal policy. And I like this kind of in terms of the cybernetic perspective that, in some sense, the optimization process has an implicit relation to the future rather than explicit. So in this sense, this is sort of a bit explicit because I kind of propagate the reward information from the goal back to the start, whereas here, I can kind of selectively optimize the start location without knowing in the future what yet I'm going to do. And I sort of have a sense of that sort of consistent with sort of an intuitive style of planning and awareness. Another nice thing about that kind of perspective is that it sort of does these rollouts. So here what I'm plotting is sort of the density of states as it converges on the goal here. And what you can see is that instead of, in contrast, the previous example I showed you where this whole room was active first, now the first thing it does is optimize the kind of trajectory near where the agent is. And the other thing I'd kind of point out is sort of this, what I'm referring to is like inference precision here, is that the policy is not optimized anywhere else except off the kind of main trajectory from the current location of the agent to the goal. So in a sense, it's sort of like not wasting resources, optimizing policy at states that it doesn't actually, is not going to be occupied in the future. So it's this kind of weird recursion that is sort of like figuring out how to do it while also doing it in a way that's sensitive to what it's kind of optimized in the future, in some sense. Okay. All right. So a bit of a pivot now.
Before you go on, so does that mean that if the environment changes, it is not going to be able to adjust quickly to that?
So there is a separate mechanism to do more kind of flexible adjustments, which gets more into technical detail. But essentially, one thing we're finding, because kind of for theoretic reasons, let's say I want to express the structure of this state space to the model. What I can actually do is express sort of like a basic kind of like a pure box with no barriers or rooms to it. I have these gradient structures, and then I can like inject or input to the model information about where the walls are and stuff like that. So in some sense, you can think a bit about like what's like absolutely stable in the environment versus what changes. But yeah, you can do things. For example, if I optimize this environment and then I put a block here, it'll kind of go the other way and stuff like that. So it's kind of interesting that way. Yeah. Okay. So yeah, so kind of just to summarize that, I think it's kind of interesting to draw on this kind of cybernetic kind of perspectives about like, trying to think about like a strong anticipatory kind of reasoning algorithm, which, I'd argue kind of, at least in these initial Petri dish style kind of analyses sort of, seems to produce some sort of these emergent properties of kind of expert human reasoning. And it's sort of like, think about, think of this as a kind of inverse word line model. Word line being like, you have to kind of map out all the paths, and then you're doing gradient descent over that kind of representation. And, that's maybe kind of an interesting, more general principle to think about. One thing, maybe it's important in the, for this is like, what you're taking a gradient with respect to is not the transition structure in the environment. It's like another kind of representation that's induced from this path space perspective, which I think is sort of an important distinction. Anyway, as a segue, I was going to talk a little bit about replay to talk about another project that I think is quite relevant to people here. But long story short, one can argue, as we did in this kind of submission, that these kind of situationally focused activations sort of look like what I call replay in the brain. So hippocampal replay, which Ida mentioned already. Here's an example of it. It's a very robust phenomena in recording cells in hippocampus. But basically, in this picture, this sort of top-down view of a maze, there's a rat here, and you get this kind of like non-local reactivation. So like cell population activity in a particular area of the brain is sort of activating position representations away from the animal. If you've never seen that before, it kind of looks like this. So the animal is here, you're recording cells in the hippocampus, and you can decode what position the cells are representing. So it's tracking the position of the animal initially, and then it kind of goes non-local. So it's very quick, you can see it, but basically it kind of sweeps away from the animal. And I think, some work I did in that space is like thinking about kind of contextualizing the many different varieties of hippocampal replay. In particular, I wanted to point out these kind of super diffusive structures in the replay, which is, I think, very consistent or, and definitely the ballpark of what Peter talked about in terms of like patch foraging, so on and so forth. And that led to some kind of work where we kind of distinguished between like kind of ordered and disordered types of replay, which has been seen in healthy mice and also mouse models of schizophrenia, which in turn led to an idea that I think has been touched on by various people here that I wanted to kind of reduce to make the connection explicit is, can we detect such internal disorder in humans using language models? So I kind of worked with Matt Noor when we were both at UCL He's a psychiatrist and very interested in kind of thought dynamics and in generally as a phenomenological entity, but also in terms of given his background as a psychologist, as a diagnostic for thought. So what's interesting was that there are many ways, for example, the DSM criteria for characterizing what we call formal thought disorders as a model of psychosis. And the key thing we want to kind of zoom in on here is focusing on formal thought disorders rather than content thought disorders. So content thought disorders would be kind of like a hallucination or something like that, confabulation, so on, so that. Formal thought disorders, something about the structure of your trajectories of thoughts, okay? So there's a big distinction in psychiatry, right? So like the formal thought disorder criteria are things like incoherence, which I think Jacob touched on, disconnected ideas, tangentiality, even verbal impoverishment, hence why the semantic foraging task is called a verbal fluency task. And essentially wanted to get a quantitative approach to this. So we did the task that Peter already introduced, and we did it in controls and people with schizophrenia. And I'll just kind of go through this quite quickly, just to make the connection to what we discussed more broadly this meeting. So you take word embeddings that Jacob already described. This is from word to vec, which is one of the models he explicitly introduced. And you can do these kind of semantic similarity analyses. What you find is, for example, that patients who perform worse at this task kind of tend to jump more than controls. For example, one interesting trajectory, semantic trajectory produced by a person suffering from schizophrenia was sheep, cow, horse, and he went to bank. So I'm wondering if anyone is from London might have an idea why they went from horse to bank. Okay, so in London and the UK in general, there's a famous retail bank whose icon is a horse. So if you do the kind of word embeddings, do this trajectory type analysis, which you can compute sort of the extent to which different populations, either control participants or people or patients, are traversing semantic space in an appropriate way, and to what degree are they optimal in doing so. Long story short, you can come up with these divergence measures, which are very kind of Todd Hillesian in their kind of analysis style, to show that compared to shuffling all the data, compared to controls, that patients are basically worse at constructing kind of efficient trajectories through the search space. And you do the kind of community structure analysis, which I think Peter certainly talked about, where you take the word embedding vectors and cluster them. So you got like, the kind of safari animals, hippo, cheetah, tiger, all that kind of stuff, aquatic animals, fish, whale, shark, and so on and so forth. And basically you can kind of work out, to what extent are different people sensitive or not to the kind of this kind of semantic clustering structure in the state space. I know I'm going through this quickly, but just give the headline. And so people, suffering from schizophrenia sort of like jump more between clusters, and they jump back and forth between clusters more, right? Suggesting some sort of like turbulence in their kind of internal thought dynamics, which is sort of quite consistent with the sort of mouse models of hippocampal replay for schizophrenia. So that could have, led to, just to summarize that, we had kind of mental trajectory tracking using language models. This is a very simple variant of this, where because we're using individual words, we don't have to do any kind of more sophisticated kind of topic modeling style approaches. Like Jake describing, is super interesting to think about, maybe people with schizophrenia talking about their lives in general, and then using these sorts of strategies to kind of extract trajectories in their narrative structures, and maybe, one hypothesis whether we can kind of replicate these sorts of effects. When, for example, people with schizophrenia have a hard time kind of like planning their future behaviors, that leads to all sorts of problems for them, and so on and so forth, even though they're kind of, generally speaking, very intelligent and creative people. Okay, and then the kind of final study that I really want to get onto is more back on the theme of kind of human expertise, is kind of looking about sort of dynamical trajectories through some kind of internal thought space, but during planning. So for that, we turn to the City of London. So this is a map of London, obviously. And what we've kind of schematized here is a bunch of possible different routes that you could take through the city of London. London is a very large state space. It's at least kind of 26,000 streets. I think the actual number of states we had on this model of London was something on the order of like 40, 50,000. And what we did in collaboration with Hugo Spears at UCL is invite taxi drivers to kind of mentally navigate around the city of London. So what we did is essentially, Ava approached them at this what's called a cabman shelter, which is a kind of an iconic landmark and very well. I don't think it's that well known, but if you spend some time in London, you'll see them everywhere. But basically, these are little shelters where, because the taxi drivers by law are not allowed to kind of leave their car at a taxi stand and go to get like some food or something like that. So they have to bring the food to the taxi drivers. So they built these little cabin shelters that serve kind of like sandwiches and stuff like that. So you can always find them, kind of hang around here, and you can approach them and entice them to do some experiments with sandwiches and stuff. So that's what we did. So the kind of type of data we would elicit things I would ask them, like, please call out the run. So taxi drivers call transferring a passenger from one location to another. It's called a run. So they'd ask them questions like, please call the run from Royal Oak to Clapham High Street, and then they would just verbalize it, and you get this kind of verbal trace of their kind of thought process, and you can segment it and kind of extract sort of like response time. So how long does it take for them to think about to produce each of these words as they navigate across the city? So we kind of look like this. You got a start location, Burleigh Street. You're getting a target, Marble Street. They'd have to do some sort of like they'd have to kind of verbalize what they're going to do. You can see this sort of like pauses and so on as the taxi driver is thinking. It's quite a difficult task, as you imagine. I think what's interesting about this cohort is kind of a unique population because these taxi drivers are not allowed to use Google Maps. They have a very strict training protocol. They've trained for years to be able to get a taxi driver license. So they really have to come up with some sort of strategy to internalize the City of London in some kind of sophisticated way, particularly because there's this huge time pressure on them, right? If you get in a taxi, you can't, the taxi driver can't sit there for 10 minutes figuring out like how to read a map or something and has to, let's get going. It's just some sort of very sophisticated strategy. And you can break down the data into kind of like an offline planning phase, which is like, when the taxi driver thinks before they even start verbalizing what to do, which is kind of like a phase I'm very interested in. And the kind of like online phase where like in between each word they produce, there's some kind of like variation in the pauses. Okay. So, one thing you can check is that there's a anti-correlation between offline thinking time and online thinking time. For example, if the taxi drivers spend more time thinking offline, then they spend less time on average thinking online, suggesting there's some relationship here. What we did is we broke down the elements of the London state space into kind of different features. For example, you can imagine there's like a trajectory from this origin location to this destination. And I can think about lots of different possible ways of kind of interrogating this trajectory and defining different types of environmental, spatial, cognitive, theoretical variables that could be influencing their reaction times. So for example, one metric we're using is sort of like the distance, the direct distance from the destination to the origin. Maybe one question is whether that is influencing their ability to recall different states. Another measures, which we'll see in a moment, is sort of the measure of their total distance along the route. Let's go here, which obviously is correlated but not completely with the direct distance to the destination. We also kind of extracted different metrics like angular deviation, for example, segment-based destination price, for example, angular deviation between your current kind of turn in absolute sort of London space and the destination versus the angular deviation between the direction you're going previously and now your new direction. Other variables like the segment distance and so on, which is reflective of the actual experienced transitions in the London state space. So some of the variables that turned to be, we tried kind of a large analysis. We tried like a bunch of different variables, like focusing initially on sort of embodied spatial variables that kind of came out as significant because it was quite interesting in terms of like the theories of spatial navigation and in particular, basis of spatial navigation. For example, the street segment length turned out to be an important factor in modulating their reaction times. So taxi drivers would take longer to report a street, or report after a street that was longer rather than shorter. Personally, that kind of surprised me a little bit because one could imagine that from the taxi driver's perspective, one could abstract that away and work with a pure kind of like graph-based representation. That did not seem to be the case. There seems to be some actual residual effect of the actual spatial structure of London in their kind of planet dynamics, which is kind of interesting. Maybe to some extent that's caused by your inability to overcome, is like a physical or neural constraint of your spatial cognition network, that's the format in which you have to encode this information, and sometimes you can't avoid it. Another interesting, I think, variable is the angular deviation to goal was a significant modulator of reaction times. For example, if the taxi driver was oriented this way and then, switched to orient this way, and the orientation of this transition was at this angle, was at a greater or less angle to the goal, that would cause the taxi driver to slow down. So for example, if the taxi driver is kind of facing away from where actually the goal is, which might be sort of behind him in his virtual navigation in his mind, then that slowed down his reaction times. What did not slow down his reaction times was the kind of segment, I kind of mentioned that also we imagine there's a segment-based angular deviation, which is sort of the angular deviation from segment to segment, that did not slow down the reaction time. Maybe consistent with the idea there's some sort of like vector-based navigation towards this goal state going on. Another variable that I was slightly surprised to see being significantly represented in the reaction times of the taxi drivers was the total streetwise distance to the goal. Again, one can imagine one could abstract London in some sort of graph-based representation, which removes that feature of the London state space from sort of a more abstract representation. That did not seem to be the case. It seemed like the kind of total distance of the trajectory was a significant modulator of reaction times in the sense that the longer the street by segment, total segment length, the kind of longer it took the taxi drivers to produce a route. Sorry, yeah.
Yeah, just one quick question. So did you ask them to abstract away things like traffic and considerations like that, to really focus sort of like on basically the things that you're capturing in your model, or did you not need to account for things like that in order to explain the planning choices?
So we didn't ask them explicitly to abstract away. Yeah, it's a good explanatory question. We didn't ask them to strap that away. We just tried to control for it by when we approached the taxi drivers at the cab shelter, we said, imagine you are picking up a passenger at 11 a.m. on a Monday. So it's all, it's sort of supposed to be all the same context for them. Yeah. That kind of, maybe just to use that to bootstrap another point that I think is maybe interesting to think about, we did not investigate in this kind of study, is we sort of assumed that all the taxi drivers sort of had the same training, they would think about it in the same way. This is sort of a fixed effects analysis. And we also assume that the London state space is essentially homogeneous with respect to taxi tasks. So like the pickup and drop down locations are all uniform. Obviously that's just not the case. So like train stations and stuff like that should have a much higher pickup rate and so on and so forth. We do have the data to maybe integrate that information and have a sort of like more kind of nuanced perspective. Thank you. But we didn't, let's say it was just maybe a lot to do for one study, so that's maybe an opportunity for follow-up. So yeah, just to contrast that point with potentially another approach to representing total distance to goal, which is the direct Euclidean distance as the crow flies. That did not modulate the reaction time of the taxi drivers. And I think what, maybe was suggestive of the fact that the kind of segment-based distance to goal and the angular deviation to the goal and the individual segment lengths all kind of modulated reaction times suggests that there's some sort of embodiment in their mind somehow of the actual London physical environment rather than sort of like operating over some kind of purely abstracted graph representation of the environment, which is, I think it's interesting whether that's like, is there sort of normative perspective? Like, is there some particular reason to do that? Maybe to the fact that they're trained to account for variations in the density of traffic along the routes. They have to think about that in their natural form of planning. It's something we're not capturing. Or it could be sort of like a non-normative issue where it's actually just a limitation of the spatial cognition network. They can't kind of sort of escape the kind of environment that they kind of operate in. Sorry, yeah.
Did you have a chance to compare it to Google Maps?
Yeah, we did some of that.
Is it the same?
Interesting. So I would say that the mean taxi driver distance, or sorry, the mean taxi driver route was approximately consistent with like a Google Maps result. But I would say is there was quite a lot of variability across taxi drivers. So they definitely had the preferred routes and so on and so forth. Yeah.
Did they try to minimize time or distance?
We kind of only measured distance, and because we sort of like tried to control for time in terms of trying to encourage them to kind of normalize the density of traffic and so on and so forth. But I think it would be very interesting future approach to, give them different contextual scenarios like, okay, it's 5 p.m., it's rush hour, how does that affect their trajectory and so on and so forth, yeah. So.
I'm trying to compare this back to where you started. With this study, are you also looking for a systemic law? Because here you are asking people to do this planning all ahead of time. Mm-hmm. So I'm wondering if you think you can get at a systemic law this way, or if you could have gone with the cabbies on the route as they were actually driving it, where they aren't necessarily planning it all ahead of time, would you see something different behavior that is more systemic law, that is more, adjusting to the conditions as they're moving towards the goal?
Yeah, it's a great question, and maybe I can answer it in the context of this slide. We're going to try to jump back to the modeling. As you said, in this situation, we kind of force them to kind of plan ahead. What we kind of aim to do is sort of like take an element of the sort of planning approach that I described, the systemic law type approach. And the way I kind of think about it is like, it's like they probably, order their kind of planning process. So for example, I think it's clear the fact that the reaction times, the offline phase, and how it modulates the online phase, they're actually verbally reporting routes, that there's some kind of separation of the, I'd say, the labor of planning across these different phases. So in some sense, there's sort of like a virtual online planning process as they're verbalizing as well. But I do agree with you that I think that is and I think that's more consistent with this sort of global systemic law approach you described versus the situationally focused one, which is the one where I can add this on a higher order constraint, which basically says you can start I'm planning so that you can immediately start moving. And I think it'd be very interesting to compare those two different scenarios by going back to the taxi drivers and going with them on the route. Just a more expensive experiment because you have to pay them to, anyway. But yeah, okay. And I should say as well, the model I described at the start, we did not run this model for the London state space. For a couple of reasons. One is as kind of a first pass approach, it was enough work to sort of get the get the data, get it set up, and so on and so forth. And essentially, we thought this more kind of like descriptive approach, comparing kind of variables ready to kind of like theoretic models of planning versus sort of the kind of embodied spatial sense of the environment is like a first pass. But what I can tell you is that we sort of, again, took this sort of like gradient descent perspective. Okay, thanks. Where we kind of imagined instead of like, the taxi driver optimizing their planning process, their kind of, type of systemic type thinking, let's say, for one particular start and go location environment, we sort of imagine that they kind of consider all possible start and go locations, and really what they need to do is sort of refine from any possible set of world paths and on-state space to like one path they're going to actually drive on. And one way to maybe approach that is just considering all possible paths as a measure of uncertainty in which path they're going to take is like the path entropy. So it's just a quantitative measure on, given a particular graph or network, you compute the uncertainty in the distribution of all possible paths in state space. And then what we imagined is that, well, potentially what taxi drivers focus on, particularly in that kind of offline period initially, is sort of like to minimize that path entropy. They kind of want to take the kind of biggest gradient descent steps on that path entropy, which when you break it down mathematically, leads you to kind of things like you want to target states with high SR, which we spoke about previously, and high local transition entropy, basically the degree of the node at which you're at. So for example, this particular state has a high SR because from a start location you have to pass through it. This state has kind of a higher local transition entropy because there's a lot of states connected to it. In some sense, if you target these sorts of states, you can kind of most rapidly decrease your uncertainty over what path you're going to take. So I'm going to say it's not the model I described at the start, but it's sort of like initial step in that direction, particularly in the multitask setting, which is where the taxi driver, we assume the taxi driver in. So we kind of compare these types of variables and how they relate off the offline phase, when the kind of taxi driver is sort of thinking or ruminating without even talking, and then kind of online phase where as they produce a description of the e-route. Interestingly, if you do a model comparison, I think I have to finish up, let's go quickly, you actually see the best fitting model contain interactions between these kind of SR and local transition entropy, like complexity and probability of state being encountered, interactions between those features of the different states being verbalized in this online phase, interactions between those reaction times, and how long they spend thinking the offline period. So basically what kind of seems to happen, and you'll see it here, is that the taxi drivers, if the offline period is longer, they specifically target states, they specifically reduce their future response time or call it time for states that have kind of high probability and high complexity. And that's something that is at least consistent with this sort of prioritization based on gradient descent and path entropy. All right, and the kind of the basic idea here is that imagine there's some sort of sequence of states that the taxi driver has to produce. They sort of like prioritize certain states, maybe sort of kind of a hierarchical way based on these kind of complexity or these path entropy type measures, gradient descent path entropy, so that you kind of like push them for processing during this initial offline period so that you're faster in the online period. And I think I'll leave it there, yeah. Thanks.